Good morning and welcome to this EDA Playground live webinar talking about static and automatic lifetimes in SystemVerilog. So this is a live webinar. I'm speaking to you live now from the UK, and I'm going to be using the EDA Playground website as to demonstrate some of the things that we're going to look at. So I'm going to start by just briefly introducing EDA Playground itself. So if you've not come across it before, EDA Playground is an online IDE. You can type your code into these panes here and then run your code as well. And hopefully you can see the URL in the address bar at the top there. So it's www.edaplayground.com. So there's all sorts of things that you can do with EDA Playground. As I said, you can type your code into these panels and run it. Now, it wouldn't be very interesting if you had to watch me type a bunch of code into EDA Playground. So one of the things that you can do is save your code, and there are also a whole bunch of examples, and I'm going to show you one of those to show you what else EDA Playground can do. So here's a very, very simple Verilog example. And as I've just said, we can run our code by clicking the Run button up here. And if we click that, the output of the simulation will appear in this pane at the bottom. You can see there's some stuff has appeared. And this was run using Oldec Riviera Pro, but if you look in this box here, you can see that there are 4 commercial simulators available on EDA Playground, Riviera Pro, Excellium, Questa, and VCS. There's also some synthesizers and some free simulators and synthesizers as well, and also some other languages, related languages as well. So you can run your code, you can look at the output of the code here. There's also a simple waveform viewer. So if you click this box over here and run it again, then a simple waveform viewer will appear. Just let it run again. There you are. You can see there's a waveform viewer. For some reason, it's come up as analog. But you can change the radix, so probably hex or something like that would be more interesting for the code that we're looking at. And you can expand buses and do the kinds of things that you'd expect to be able to do on the waveform viewer or on a simulator that you are running on your own computer. So it's a simple waveform viewer. There are cursors, there's 2 cursors you can see, and so on. So you can also save your own playgrounds, and there are various other things. There's quite a sophisticated editor, so you can do the normal things that you'd expect to do, like cut and paste. You can automatically comment lines just with a control, and there's also column editing as well, so you can do various things like that. So that's EDA Playground. It's completely free to use. You just need to register. You can either register with a Google account, which will give you access to some of the functionality, or you can register with an email address, which gives you access to all of the functionality. But your email address can't be some freely available email address, so it needs to be like a university or a company or something like that. So that's EDA Playground. Let's get started with the webinar, static and automatic lifetimes. So you may have seen the keywords static and automatic appearing in the code that you've seen. And so that's what we're going to talk about. And if you were to look at the SystemVerilog standard, IEEE 1800, sometimes we call it the LRM, the Language Reference Manual, you will see that this choice between static and automatic is referred to as the lifetime. And the lifetime is a really good name for this, because the difference between static and automatic is entirely the lifetime of the variable. So when it's created, when it's destroyed. And basically, a static variable is created at compile time, whereas an automatic variable is created when it's needed and then destroyed, so it's created at runtime. So a static variable always exists, and an automatic variable exists temporarily. And you might be thinking that, well, I've come across the keyword static in other languages, so like C, for example. And if you know a little bit of C like I do, but perhaps not as much C as I know SystemVerilog, you might be thinking that static is one of those variables that remembers its value between function calls or something like that. If you'd asked me what static meant 20 years ago, that's what I would have told you. But actually, that's just a symptom. That's just a side effect of the fact that a static variable exists all of the time. So all of the other sort of ideas that you might have about what static variables are, that's probably just symptoms to the fact that static variables always exist. And in SystemVerilog, all variables declared outside classes are static by default. So if you want a variable to be automatic, then you have to declare it. But there are certain situations where you also have to declare it to be static as well. And you're probably aware of hierarchical names in SystemVerilog, so that is where you can refer to a variable that's in a completely different module by saying this module dot that module dot some block dot some variable. They can only reference static variables. One thing that I need to say before we move on is as Dave said in the introduction, you're very welcome to ask questions. What I will do is attend to the questions at the end of the webinar, and just an appeal, if you do ask a question, please do, please make sure they're self-contained. So if you ask a question, something like, what did you just say? Then it's not going to mean anything at the end of the webinar. So if you could give the slide number or the slide title, because it doesn't actually have a number, does it? The slide title, that would be useful. So that I can read the question in isolation. And the second request, which is going to contradict the first one, is make them snappy. It takes quite a long time to read them. So if it's long-winded, I probably won't answer it because it will take too long to read it and understand it. So I appreciate that English isn't going to be the first language of everybody listening to this. But please do your best to make them short but self-contained, and then that's more likely that I'll answer them. We will answer all of the questions by email. We'll send you a summary of all of the answers to all of the questions afterwards. But if you want it answered live, it needs to be short and sweet, but completely understandable. So I think, did I say this? Yes, variables outside classes are static by default. So variables inside classes are automatic by default. So let's have a look at some code. Here is some code with a static variable. And because a static variable is created at compile time, a static variable will be initialized at compile time. And that's one of the key things that you need to be aware of if you're trying to decide whether to use a static or an automatic variable. So if you look at the code here, you can see that we've got a loop, a do while loop here, and inside the do while loop we are declaring a variable called count, and we are initializing it to 1. And because the variable always exists, because the variable was declared at compile time, then it was initialized at compile time. And because of that, that initialization will only occur once even though the variable is declared within the loop. I won't say any more because that will spoil the fun when we look at the EDA Playground example in a few seconds. But before I do, one thing that the standard says, the LRM says, that even though variables are static by default, if you initialize a variable, you must explicitly declare it as static. So what that means is we needed to say this keyword static here, and if we didn't have this keyword static here, it ought to be an error. Why do I say ought? I say ought because actually simulators have different opinions about that. So it ought to be an error, but not all of the simulators actually flag it as such. So let's have a look at this code in EDA Playground. So what I'm going to do is open it in a new window. So here's the same code that you just saw on the screen, apart with a couple of extra commented out lines, which we'll come to later. So what we're going to do any minute is run the code, and what you need to do is predict what is going to happen. And you probably can do that fairly easily. Whilst it's not relevant to this webinar, you might want to think about what the final value of count that is going to be displayed is as well. So there's two questions. One, what is going to happen? Hopefully fairly straightforward. Two, what is the last value of count that's going to be displayed? So the wait is over. Let's run the code and see what happens. So you can see that the key thing, and the thing that is relevant to this webinar, is that the value of count increments, it changes. Even though we are initializing the value of count within the loop, its value changes. And that is because count is a static variable. And so it was initialized at compile time. And so this initialization doesn't reoccur every time around the loop. And the second supplementary question was, what was the final value of count? The final value of count is 10 because we're going for 10 nanoseconds, and so you can see that the final value of 10. But that was a bit harder to work out. So what we'll do is go back to the presentation and move on to the next slide and have the same block of code, but this time it says automatic. So before it was saying static here, now it says automatic. And so now the variable count is created when required. And basically it's going to be created and destroyed every time around the loop, which means that the variable count, and this is the important bit, is going to be reinitialized each time around the loop. So if we go back to our code and change this keyword static here to automatic, and I think you can probably predict what's going to happen. So let's run the code again and prove you right. There you go. Not very interesting, is it? Because we've changed the value from static to automatic, the variable is now recreated each time around the loop and destroyed, and so it is initialized each time around the loop. Now, you can declare a module to be automatic if you want to. So you can add the keyword automatic here. And if you do that, then if a variable is allowed to be automatic, then it will be automatic. And so here we've we've got a variable here which is declared outside the loop. This is still static because it's declared at time 0. I mean, how could it be automatic? But this one within the loop is now automatic, even though we haven't said so. But we're now opening a little bit of a can of worms. That's a British English expression. We've entered a bit of a minefield here, because by removing the keyword static, this is now illegal code. And so the simulator ought not to allow this, but we could not initialize this. So if we just said int count semicolon, then the variable would be automatic but not explicitly initialized, and that would be legal. And you might be wondering what value count would be initialized to, and the answer is 0. So if we go back to our code here and uncomment this keyword automatic here like this, and well, we can uncomment that, but it doesn't make a great deal of difference. And we've got a variable here, so we'll uncomment it like that. So we'll take away the automatic keyword, and then we'll get rid of the rest of the line like that. And so now count should be initialized to 0 each time around the loop. And so if we run the code again, we'll see that that is what happens. There you go. And so in other situations, then having a variable that is automatically automatic might be of interest to you. But I mentioned this is a bit of a can of worms, because different simulators, not only do they have different opinions about what should or shouldn't be legal at this point, they also behave in different ways. So if you want your code to be portable across different simulators, I probably wouldn't do this if I were you. So going back to our presentation and moving on, another key area where automatic or the distinction between automatic and static is really important is within tasks and functions, particularly tasks. So if you don't specify whether a task or a function is automatic, or whether a variable that is declared within a task or a function is automatic, then that variable will be static by default. So if we look at this function here, you can see we've just got some function f, and we've declared a variable called j within our function. That variable is static. That might or might not be important, but if you did write your code in such a way that the distinction was important, you would find that that variable would be static. Whereas k, because we have explicitly said so, is automatic. Now, what we could do is add the keyword automatic after the keyword function. And if we do that, then the variables declared within the function are now automatic. And so k is automatic and j is static because we said so. And I see this is actually I think we probably needed to say int or something here. I suspect this is a typo, I'm sorry, but I've just noticed that. But anyway, assuming that we add the keyword int here or some other type, j is static because we said so, and k is automatic. And the same with tasks. So here's a task, and we've got a variable j here, so that's going to be static, and a variable k here, which is automatic because we said so. But if we add the keyword automatic to the task like this, then j is now static because we said so, and more importantly, k is automatic. And again, we needed some kind of type here, sorry. So where this begins to really become important is with tasks, and particularly with the arguments to tasks. So if we have a function like this, then any variables within it are going to be static, and quite importantly, I is going to be static as well. This variable I, which is an input, is static. Whereas over here, by adding the keyword automatic to the function, I is going to be automatic. And the same with the task as well. So this variable here, I, is going to be static. And this variable I over here, by adding the keyword automatic, is going to be automatic. And you'll see in the following examples why that might be important. So here is a static variable within a function. So we've got a function here. We haven't said whether it's static or automatic. And we've declared a variable inside, which we're initializing, and then we're returning the value of that variable incremented by 1. And you can see we've got a little bit of a loop here. We go round 10 times roughly, perhaps it's 9 times, 9 or 10 times, and we are calling this function, f, and then we're printing out what we see. So let's have a look at that in EDA Playground, and then we'll go and run the code. Now, nothing happened. Why is that? That's interesting. Let's try again. I think I selected the wrong thing. So here is the code that you were just looking at on the slide. And so just give you a couple of seconds to think about what is going to happen here. I think you can probably work it out that something interesting is going to happen. Otherwise, I wouldn't be showing you the code. So we click run again and see what happens. There we are. You can see that f has incremented, or the return value of f has incremented. Why is that? That is because I is static by default. So I is behaving like one of those variables in C, for example, that you may have come across. Whereas if we, let's just add this keyword automatic to our module, have a think about what you think might happen now. Let's run it again, see what we get. And now our variable is automatic, which is could be important. It's even more important with tasks. So let's go to a task. As I just said, if you have a static task, so either in this example here, we've explicitly said that the task is static, but even if we didn't have the keyword static in our task, then it would be static by default. You can see that from what I said before, this variable I is also static. And our task waits for 2 and then displays the value of I, and you can see that we're calling it immediately with the value 5, and then we're waiting for 1, and we're calling it again with the value 6. So let's have a look at what happens here. So here's the same code, so just give you a little bit of time to think about that. And then let's click run here. And I don't know what you think is going to happen. I guess you probably think that something surprising might happen, else I wouldn't show you the code. So we called the task at time 0, we called the task at time 1, and we called it at time 0 with the value 5, we called it at time 1 with the value 6, and it displayed 6 both times. Interesting. Why has it done that? It's done that because the variable I is static and it was declared at compile time. And so each time you call the task, there is only one variable I because it was created at compile time. And so when we call the task at line 12 here, the value of 6 overwrites the value of 5. And so when the task prints out the value of I, then it prints out a 6 instead of a 5. And as I was just saying, everything is static by default. Everything that's outside of a class is static by default. And so if I take the keyword static out here, you'll see exactly the same thing happens, and it's only going to behave itself as like the I don't know how good your English is. We tell children to behave themselves, we mean behave well. It's only going to behave well if I add the keyword automatic here. Now when we run it, as hopefully you were expecting, the first time we call it, it prints out 5. The second time we call it, it prints out 6. And the reason is that now the variable I is created when it's required, i.e. when the task is called, and then destroyed when it's done with, when the task is finished, when the task returns. And so each invocation, each calling of the task has its own copy of I. And then again, if you're you can probably guess what's going to happen if we do this as well. So we'll do the same thing, and it's going to behave itself. And so the first task call, prints a 5. The second task call prints a 6. So I personally would recommend making it a habit that whenever you have a task, you add the keyword automatic like this, because I'm guessing, I can't see inside your head, but I'm guessing that if you didn't know about this, the behavior that I just showed you was not what you would have expected. Whereas if you always make your tasks automatic, then they are going to behave themselves unless you really want that strange static behavior. So we're nearly there. What about in classes? Well, as I've already said, a variable within a class is automatic by default. So here we've got pretty much the same example, but this time our task is within a class. So we've got the class C here, the task T within it. We haven't said whether it's automatic or static or anything. We're constructing our class, and then we're calling the task with the value 5 at time 0 and the value 6 at time 1, just like we were doing before. I'll give you a couple of seconds to think about what is going to happen given what I've already told you. It basically works. It behaves. Why does it behave? It behaves because variables within a class are automatic by default. So here's the same function that you saw a few slides ago, and similar code, the difference being that the function is now wrapped up inside a class. And so again, I think you can probably guess what is going to happen here, that I is now no longer a static variable. So if we run our code, you can see that the value of I is reinitialized to 0 each time. We could add the keyword static here and see what happens again. And now it works. It's behaving like that kind of variable that remembers its value between function calls. Why is it doing that? Because it has a static lifetime. It was created at compile time. It always exists. So that's the end of the talking part of the webinar. We can I'll have a look at the questions. I can see there's 20 questions or something appeared in the chat. Thank you very much for asking those. So I'll turn my attention to those in a second. But before we do, a little bit of advertising. So If you've not come across Dulos before, we are a training company. We deliver training courses in system, IC design and verification, so SystemVerilog, UVM, formal, System C, that kind of thing. We also deliver courses in more FPGA type things, so VHDL, Verilog, also SystemVerilog, of course, for FPGAs, Tickle, Intel and AMD FPGAs. We also have embedded software courses, so you can see various things here. We've just been introduced Android and Rust and Zephyr, for example, and we also deliver courses in Python and AI and machine learning and this kind of thing as well. And the material that I was showing you today, or the concepts that I was showing you today, are all taught in our comprehensive SystemVerilog course. So this is a course that teaches you everything you need to know about SystemVerilog. It does assume that you know some Verilog before you start, because SystemVerilog is a huge language. And you can see on the slide there that there are the dates of forthcoming courses, and also there is a URL which leads you to more details about the comprehensive SystemVerilog course on our website. So thank you very much for listening. I'm just going to hand you back to Dave, who will talk to you for a short while whilst I start having a look at the questions.
Great stuff, Matthew. We've had a few questions through, but if there are any more, please feel free now to ask away. But just before we get through to answering them, I'd just like to say we'd be grateful for any feedback you've got on today's session. Please use the exit button on the GoToWebinar interface when you leave and complete the survey. So we'll tackle as many of questions as we can in the next 20 minutes or so. If Matthew doesn't get to your question, don't worry, we'll compile all the unanswered questions into a Q&A log and we'll send that out to everyone, along with links to all of the playgrounds that we've used today within the session and the full recording of the session. Right, let me hand it back over to Matthew.
Thank you, Dave. So I'll switch back to the slides and then we can have a look at the questions. So static variables can't be traced in waveforms as well. That's news to me. If you go back to the very first slide, that by default variables are static, and so in Verilog, certainly earlier versions of Verilog, I think all of your variables were static because there wasn't any concept of automatic, but we still had waveforms. So I'm going to put this code on the screen again. So just bear with, we'll open it up again in EDA Playground. What did I do wrong? I clicked the wrong thing. And what we'll do is we'll click Open EP Wave after run, and we're going to get what I call the world's most helpful error message, because it's going to tell me that there's no VCD file. And it very helpfully tells me the code that I need to add in order to dump out waveforms. So I just copy that and add it as another initial block here, like that, and run it again, and now we'll get some waveforms. We know that the count is 1, and there it is. So I'm not sure what you were thinking there. You can see static variables in waveforms, and I've sort of argued why that is the case. Unless you're thinking of static variables in classes, I don't know. You certainly can't look at that on EDA Playground because the waveform viewer is not sophisticated enough to be able to see variables in classes. But
if you just look at the bottom, Matthew, you'll see that question's been amended just at the bottom.
Okay, meant it was automatic, can't be received in waveforms. Oh, I don't know. Well, let's have a look, shall we? Okay, we'll get rid of that and change it to automatic. That may be the case. I don't know. I might be about to learn something. It's not there. It does seem to be the case. Yes, you can't look at automatic in, certainly not in EDA Playground. No, it's not there anymore. That does sort of make sense, doesn't it? But I've never come across that before. So there you are. We've all learned something, or perhaps only I've learned something. So what's the next question? Why is it that inside the automatic module, we are initializing count, but not adding the keyword static? So not exactly sure what is being asked there. So if we do something like this, then as I say, this is technically illegal. I have a feeling this simulator does say that it's illegal. Let's have a look. No, this simulator's happy with it. So it did depend entirely on what simulator you're using, but technically that's illegal, and you are supposed to specify whether it's static or automatic. So for example, if we say static there, it will now run and behave like a static variable. So I have a feeling I might not have understood the question there. So ask another one if I've not answered it. What's the difference between scope and lifetime? That's a really good question. And it's something that I wish I'd added to the presentation, because we had exactly the same question this morning, or earlier today. And basically, lifetime is a time thing, and scope is effectively a space thing, for want of a better word, without wanting to come too relativistic. Einstein is not involved in this. So basically, well, if we look at this code here, let's look at the automatic one. The variable count is automatic, and so it exists temporarily, whereas here the variable count is static, and so it exists all the time. But the scope of the variable is only within that begin end block. So you couldn't, for example, $display count outside the begin end block. You couldn't do it here, you couldn't do it after the while loop either. It just would not compile, because it would say there's no variable called count here. So that's what scope is. Scope is where in the code the variable exists. Lifetime is when in the code, or when in the simulation the variable exists. So why is exactly code equals 0 is printed in the last example? Not sure which what you mean by that. What I did mean to say is, please can you make your questions self-contained? So because I'm going to be answering them at the end. So perhaps you might like to ask that question again, and I can answer it. Well, perhaps I can guess. I'm not sure which you mean by the last example. So do you mean literally? If you mean literally the last example of the whole presentation, that's that one. Okay, I'll answer that one, because that is the last one of the entire presentation. So perhaps that's what you meant. So if we run this, it is indeed going to print 0 the whole time. As we can see, why is that? Well, it's because I is automatic. Why is I automatic? Because it is declared within a class, and variables by default in classes by default are automatic. And because the variable is automatic, it's created when the function is called, and so it's reinitialized to 0 all of the time. The same person has said no, not to the very last. Well, if you can say which one you mean, I'll do my best to answer it. So what if the inputs are ref? That I didn't talk about ref at all. So let's go to ref. So we need to go to tasks. Let me think which one we want to go to. Probably that one's a good choice. So I'll open that in EDA Playground. And so you might not know about a ref. So a ref is, or let me take a step back. Function inputs, outputs, return values in SystemVerilog are passed by copy. That is a thing. That's a software engineering, computer science type term. And what it means is that the values are literally copied from the code outside the function or task to the code into it. In SystemVerilog, you can also add the keyword ref here. And now, instead of the value 5 and 6 being copied, this is literally displaying whatever value is there. If you can see the reason, it's like a pointer, or it's short for reference, and so it really is the value. Now, pretty sure this is not going to compile because it doesn't make any sense, does it? Variable can't have two values at once, and so we'll try it, but I think it's going to fail, and I'll then fix it. Let's have a look. No, it's not happy. The reason why it's not happy is because ref only work on automatic tasks and functions. So we'll run it again, and now it's going to work. He says confidently, it's not. What have I done wrong? Because it's, of course, I can't pass values in here. So what do I need to do? I need, just bear with. I'll say I5 equals 5 and int I6 equals 6, like that. And let's see if that works. Still doesn't work. This is the trouble with it's because it wanted to say unsigned. That's why. This is the trouble with writing code live in front of the world. There we go. So what have we done? Right, it was very picky about the types uncharacteristically for SystemVerilog. So we needed to make I5 and I6 int unsigns, just like this value here. And we have now passed in the value. So we could do a little experiment here just to show you what a ref argument is. Let's wait another one and say that I equals 7. Like that. Is this going to work? Yes, I think so. So we need a begin here now. And then we'll say wait another 2 just to be safe. $display I6, and I'm making it up as I go along here, folks. So we're taking a bit of a risk. Just tidy it up, and I think it's going to display a 7. Let's have a look. There you are. Phew, it worked. That's the trouble with writing code live in front of an audience. So that was really just to demonstrate what ref meant. And so the value, the variable I here really is I6. And so when we changed its value here and then displayed it down here, it displayed a 7. So it only works for automatic variables. Good question. So when the task was static, initial 5 is called before initial 6. Why is it print 5? Why is it print 6? That was sort of the point. Let's go back to the slide. So I'll open it again. So if we can reset effectively. So, and basically, because I is static, there is, and therefore is created at compile time, there is only one copy of I in existence. And so when we call the task after 1 here, the value of I gets changed from 5 to 6. It gets overwritten. And so when the display is executed from this call here, the value of I has been changed to 6. And so it displays at 6 with both task calls. So which situations can we use automatic tasks and functions? I'm assuming most of the tasks we use in simulation generally is automatic. Well, most of the tasks you use in simulation are going to be static, actually, because by default, tasks and functions are static outside classes. And so if you don't explicitly add the keyword automatic to your task or function, then it is going to be static. And so the inputs and outputs will be static. Any variable you declare within it will be static. And where that is, probably most likely to cause you problems is with a task. Now, if you've got a task and the inputs are static, you get this strange behavior like I've just shown you on EDA Playground now. So as I was saying, my recommendation would be to add the keyword automatic to immediately after the keyword task, unless you really wanted this really strange behavior. Can we explain automatics and forks? We can, yes. So just to show you a little bit of, again, we had this question this morning, and so I did some preparation. So EDA Playground allows you to save your code, as I already mentioned, and so I've saved one here, static automatic variable in classes. So this is a little example that I've put together since this morning. So if we look what's going on here, we've got a, no, that's not the one I wanted, sorry. Need more descriptive names. I think it's this one, apologies. So if we look what's going on here, and this is an interesting example, but it's a little bit more esoteric. So we've got a loop, it's going around 3 times, and we've got a fork join none. So that spawns a background task. And inside our loop, we are declaring an automatic variable here. And same rules apply. Our variable is being created as it's required. We're going around the loop 3 times. And so the situation there is we actually get 3 copies of this variable ID. And so if we run this, we will see that each of the 3 threads that we're spawning has a copy of ID, has its own copy of ID, and each of the copies of the ID have a different value because we initialize them to the value of the loop variable each time round. And so automatic is actually really useful when you're doing fork join like this, as you can see. So I didn't include this in the original slides because we wanted to keep it to half an hour, but as I say, we've got quite a bit of time to answer questions, and somebody asked me this morning, and so I prepared this example in between the 2 presentations. So we can't make that static. It's not going to compile because it's going to complain that we can't have. Is that true? Actually, I'm not, maybe wrong here. I'm going to reserve judgment. No, I am true. We can't make this static because there's now only one. I should have been more confident with my own opinion, shouldn't I? There's now only one variable, and we can't set one variable to 3 different values. That doesn't make any sense. So I can see more questions appearing about this, so I won't delete this, but I'll answer the questions in order. Though, mind you, this is a really long one, so let's have a look. Near the beginning, there was an example with 2 occurrences of int count equals 1. Change the second occurrence inside the loop to int count to ensure the simulator compiles. When he ran it, the result was 0 because he said integers are initialized to 0, if not assigned upon declaration. That is true. Why does the int count inside the loop not override the int count equals 1 outside the loop? Okie dokie, I get it. Good question. Right, let's open a new EDA Playground. So we're talking about this one here. So, well, we don't need, doesn't really matter whether that's automatic or not, but basically what I did was I got rid of that. Let's set it exactly as it was this, just now, and we had it automatic, and I said, well, this may or may not compile depending on what simulator you've got. So what I'll do is I'll do that, and now we know it's legal, and we run it, and as I was saying, the value of count is 0, as you can see, and the questioner is saying, why isn't it 1? And they're saying, I've understood the question correctly. Why is it 1? Why is it not 1? Because of this. And the answer is we've got 2 different counts. So we're back to lifetime versus scope. This variable count here is in scope within the module. So if I mean, I can't say $display here, but if I can't refer to count outside the module, it doesn't exist outside the module. And this variable count here doesn't exist outside this begin end block. But notice it has the same name. But just because it's got the same name, it's not the same variable. It's 2 different variables. And so this count effectively hides that count. It's a different count, but we can actually refer to it using hierarchical naming. So what I can say is $display something like, what was going to work? Let me just think, m.count. That's going to display a 1. So when have I done that? I've done that inside the loop. So it's now going to go 0, 1, 0, 1, 0, 1, and so on. Because m.count is this one here. There you go, as you can see. It's gone 0, 1, 0, 1. So hopefully that answers your question. Right, basically loop and fork. I think we've done some looping and forking. So special keywords in the SHM to capture automatic variables with Excellium. Okay, there you are. So if you're using Cadence Excellium, you can capture automatic variables, but you need some proprietary stuff to make that happen. In VMM, don't know VM, or UVM, do know that, where most things are classes, does that mean in the environment tasks and functions would be automatic instead of static? Yes, it would, because all of your tasks and functions in UVM are basically inside classes, just about, aren't they? So yes, they're almost certainly going to be automatic. Do we have to have wait fork? Not exactly sure. We go back to our, I guess I did predict that we might have more here. Well, we've got wait fork here, but that's because I stole the example from an existing one. Do we have to have it? So I guess you're saying what would happen if we didn't have this? Okay, let me try and predict it. Putting my neck on the line again. I think what this is going to print out now. Sorry, I realize I need to, let's just undo everything. So we take out the wait fork. So the threads within the loop do not start until the parent thread blocks or the parent thread ends. So because I've now taken out the wait fork, then line 15 is going to execute before any of the displays at line 10 execute, and so it's going to come out in the wrong order basically. So can you see it says join none wait fork, and then it prints out, or then line 10 executes 3 times, whereas if we put it back to how it was, it's going to come out in a different order. So now it says join none, then because of the wait fork the threads all start, so it's printed out the values of ID, and then when that finishes, because the wait fork says wait for all the child threads to finish, it then prints out wait fork. So we didn't need these lines of code to demonstrate what we were talking about in this webinar, but I didn't write the code from scratch. I stole it from an existing example, and it had those lines of code in it. So do we need it? No. Is it, does it have an effect? Yes, it does. And I think that's it,
Well,
actually.
I think that's it, Matthew. Yes,
that is
you've
it.
got to the end of the questions.
We have. So there we are. So I will put this slide up here and let Dave take over and tell me what he's going to say about it. And thank you very much for listening and for asking the questions.
Thank you for another great session. Thanks for taking the time to answer all the questions and sharing the benefit of your years of expertise with us. If we haven't answered your question, which I think you have answered them all in this session, haven't you?
I think so.
We'll compile them all in the Q&A log anyway, and we'll send it out to you with the recording of the session and links to all the playgrounds that you've been going through in the next few days. Once again, our thanks for attending today, and we hope to see you again next time. Bye for now.